I'm Jim Ratz from RF Micro Devices, and the title of my presentation is RF Power Amplifier Design for Pseudo Envelope Tracking. Can everyone hear me okay with the microphone? Okay. So I work for RF Micro Devices, and I'm based in the Cedar Rapids, Iowa Design Center in Hiawatha, Iowa. I work in the Technology Platforms Organization, and before I go into the talk, I'd like to give a couple acknowledgments to some of my colleagues at RF Micro Devices that have been very instrumental in the project, that being Andy Folkman, Nadine Klott, and Mike Kay. So start off with an outline of the presentation. I'm going to give an overview of pseudo envelope tracking, and then I'm going to develop that into some setting power amplifier load line targets for the envelope tracking PA. And then in the end, I'm going to provide some summary measurements of the envelope tracking PA along with some simulations of ET performance using the PA. So in first step, we'll talk a little bit about the motivation for envelope tracking in the cellular. My work is based in the cellular handset PA world or solution space. And as the market trends toward more higher data rate modulations, we continue to see that. So to the PA designer, that typically means higher peak to average ratio signals. And with the higher peak to average ratio signals, you can see in the, I've included a CCDF plot of a couple modulations here. The blue curve is a 3G voice signal. It has roughly a peak to average ratio of about 3 dB. And in the red and the orange are LTE signals. So in the case of a 25 resource block QPSK and a 25 resource block 16 QAM signal. And with the LTE signals, we experience a peak to average ratio that's more like 6 to 7 dB. So if you're operating from a fixed supply for the PA, you end up operating at a lower, the higher peak to average ratio pushes your PA back to a further power back off, generating lower efficiency in the PA. So this higher peak to average ratio brings into the handset solution, makes it attractive to use an envelope tracking solution and actually provide an efficiency benefit over the fixed VCC supply solution. So the overall goal is to get, as has been discussed this morning, is to get lower system efficiency, and in our phones, that's so we have longer battery life or can allocate the battery current to other functions in the phones, or for all our cool phones, we can have a cooler phone temperature. So in this slide, I'm going to talk a little bit about pseudo envelope tracking and constant gain operation. So the two plots here show gain and efficiency on the y-axis plotted against output power on the x-axis. And the plots show in the blue set of curves is a sweep of the supply voltage in increasing voltage. So in the gain curve, you can see as the supply voltage ramps up, the blue curves give higher saturated output power. And then in the blue curve, we get a collection of efficiency curves that provide, as you ramp up in power, higher efficiencies. So the reason I use the word pseudo to prefix the envelope tracking is that we're going to set up a lookup table that maps the collector voltage based on the input power of the modulation, and rather than just simply make the collector voltage just simply proportional to the envelope amplitude, we're going to actually map it to provide some beneficial effects. So in one case, shown in the orange case, is a peak efficiency approach where we characterize the PA and we come out and find the voltage at each output power that gives the highest efficiency that's possible. And then you can see on the efficiency curves that the orange curve, the peak efficiency, picks off the peak efficiencies. Well, for the corresponding curve on the gain curve, there's quite a bit of distortion in the gain characteristic in orange. The orange curve is the same data pulled and plotted for gain. We have maybe 1 to 2 dB, actually more like 3 dB of gain expansion and some gain roll-off at the top, so fairly non-linear. And our goal in the handset space is to provide envelope tracking without requiring digital pre-distortion of the RF input signal into the PA. So in a system that could provide the RF pre-distortion for the input signal, you could correct for that AM to AM distortion. But in our application, we're trying to avoid that. So we use a different technique called constant gain operation. And in this case, I plotted on the gain curve a red curve that calls out a constant gain of 30 dB. And so here we've linearized the AM to AM characteristic of the PA, so we hope to avoid any distortion due to AM to AM. But you can see in the efficiency curve that the efficiency is somewhat degraded compared to the peak efficiency case. We're operating about roughly 3% lower than the peak efficiency case for this PA. But we can choose a different constant gain operating locus of points and get better efficiency with the constant gain approach. On this slide, I've elected to choose the constant gain of approximately 29 dB for the PA. And you can see that the efficiency curve, I'm not sure how well the orange and red show up on the projector, but basically they're right on top of each other or very close to it. So by operating further into compression on the PA gain curves, we were able to get a higher efficiency while still achieving our AM to AM linearization of the constant gain approach. Now, typically the PAs are probably going to have the best efficiency when they're operated 2 to 3 dB into compression, but there are trade-offs in the system as you go further into compression. We saw this morning how it makes it more difficult for the ET modulator in terms of noise performance and some other performance parameters. So there's definitely a trade-off between how far into compression you can operate, and some of that may depend on band of operation and some of the specifications per band. But in general, you can get higher efficiency operating at a constant gain that's more compressed, but there may be some trade-off with the ET supply modulator. So the curves on the previous page is focused on the gain and the efficiency. So on this curve, this plot, I'm going to show the phase performance of the PA. So as before, the same PA was swept over a range of VCCs, and you come up with a family of phase characteristic curves for the PA. And then as we apply the different lookup table mappings, we get a residual AM to PM characteristic out of the PA. So in the red case is the constant gain approach. We end up with some phase characteristic, some phase distortion, and the peak efficiency in orange has a different phase distortion. So our approach is to choose a constant gain to linearize AM to AM, but as a side result, we end up with a residual AM to PM characteristic that we need to work with. So in the design of the PA, we have to be careful to control this characteristic so that when we operate along the lookup table path, the amount of phase distortion doesn't become large enough to limit system performance. Once again, if RF pre-distortion was applied at the input of the PA, this could be corrected, but our goal in the handset is to not require the RF pre-distortion at the input of the PA. So on this particular PA, I have some more data showing when we get later in the presentation, we'll see some of the effects of this AM to PM and how it can degrade the signal. So the last two curves, the last several slides show plots of the families of VCC data for the PA. On this slide, I'm going to change the format of the data just over to contour plots to get a little bit different interpretation of the data. So this is a contour plot of the gain in 1 dB steps. The x-axis is the collector voltage applied to the PA, and the y-axis is the collector voltage applied to the PA, and the x-axis is the input power to the PA. And you can see the gain contours at the peak at 31 dB. There's an arc in the gain contour. Not a very desirable mapping for the VCC, but once you get to 30 dB or lower levels of gain where you start getting into compression of the PA, you end up with a trend of your constant gain curves where as you go to lower input power, you go to lower VCC. So although this isn't ideally proportional to the envelope of the modulation, we do get the desirable characteristic of lower VCC at lower power. So in the next few slides, I'm going to take this contour plot and develop it into setting some boundaries for the load line targets of the PA. So I have a slide here on peak clipping, but it actually fits a little bit later, better in the presentation later. So I'm going to skip over that and come back to that in a moment. So on that same contour plot for the gain, we can superimpose on that some range of VCC that the supply modulator is capable of. So depending on the solution for the supply modulator, it may have it may be like a buck solution or a boosting solution or buck or boost. So there's going to be some range of voltages it can generate during ET operation. And even if I want to operate on, say, that first curve down, the 30 dB constant gain curve, I'm going to be limited by that range. I can't go beyond those VCCs. And if the modulation does try to push us there, we are going to clip. So I've got a picture of a little bit of how that happens here on the next slide. So this is I picked off the gain equal 30 dB contour from the previous slide. It's in blue, except mostly it's covered in red by the mapping. So in red is the mapping with the limits of VCC max and VCC min applied. You can see at point A and C, if the input power rises up high enough, the VCC max will be clipped. The supply modulator cannot generate a higher collector voltage, and at that point, we'll clip the VCC and the gain will lower. On the low end, you can also see there's clipping that might be set by the lower dynamic range limit of the supply modulator. And in the plot here, I'm primarily interested with the upper end because I'm trying to work this into a load line target for the PA. So at point B, we consider that to be the average power that the PA is going to output, or the rated power that we're targeting. In the case of my work, that was 26 dBm. So as the modulation runs through, as we run through the modulation in time, the peak, we're going to get instantaneous peaks and valleys of the modulation. We're going to follow along the red curve, and if we get peaks in the modulation that on the x-axis exceed point A, the VCC max is going to clip, and we're going to experience lower gain. So in a conservative case, if we wanted to avoid, so the clipping is going to provide distortion now into this AM to AM that we did a careful job of choosing a constant gain to try to eliminate distortion. But so if we wanted to be conservative and completely avoid that clipping on the high end, we could set up our operating point B, our rated power, so that we were below the point A by the amount of peak to average ratio of the signal. So if we had a 7 dB peak to average ratio LTE signal, we could choose to align our rated power 7 dB below that point A where the onset of clipping occurs. But in fact, I'm going to back up to the slide now on the peak clipping. We've done simulations with the PA model and the envelope tracking and the clipped upper voltage, and we find that actually we can clip the peaks and still achieve acceptable linearity performance. So on the slide here, I'm showing two CCDF curves. The one on the left is the source signal, the modulation itself. I think in this case it's a 25 resource block, 5 megahertz QPSK signal. And roughly speaking, the very high peaks, the peak to average ratio is about 6.8 dB. So this is what's going into the PA model. And then as we lower the VCC max so that we clip the max VCC, that doesn't necessarily clip the max output power, but it does make us clip gain. We can see that we can clip that peak to average ratio down to about 4.4 dB and still end up with ACLR results that are better than minus 40 dB, which is usually considered linear, quite linear for the handset PAs. So we can take advantage of that clip peak to average ratio and align our point B here closer to point A on the curve. That's going to move our VCC rated up higher And the bottom line is it's going to end up allowing us to use a higher load line for the PA, and the advantage of a higher load line is higher efficiency in the PA. On this slide, I take a little bit different view of the same contour plot. I've simply just translated the x-axis from power in dB and instead plotted it as a voltage. And what you can see now is that these constant gain contours, once you get a few dB into compression, become quite linear in appearance. Basically, we're getting the PA into saturation, and it's following just the load line theory of operation as you vary VCC. So this is the same curve as before, or a similar curve as before. The red plot is the lookup table of constant gain. In this case, it's drawn for a gain of 29 dB with the clipping on the min and max VCC applied, and we can use this to set up our load line targets by using that the load line theory between points A and B. If we want to set our point B to be a certain peak to average ratio below point A, we can simply use a 20 log square approximation on VCC to come up with our VCC rated as compared to the VCC max. So basically, our load line theory, our power is proportional to the square of the collector voltage adjusted by an effective knee voltage. And I didn't mention that before, but that was also shown in this slide. I identified an effective knee voltage that you see at the y-intercept on the VCC curve. As you go further into compression, that knee voltage tends to get a little bit lower in the empirical data, but we can use that in the equation too. So if the P peak is the power at VCC max where the onset of clipping occurs, and P rated is the power at VCC rated, we can form the ratio. And then, so basically the ratio of P peak to P rated is the peak to average ratio where you want clipping to start. So then we can calculate the VCC rated. So as an example case here, run through some numbers. If we have a 5 megahertz 25 resource block QPSK signal, and based on the simulation earlier, we saw that we could clip to about a 4.4 dB peak to average ratio and still expect decent ACLR. And then we want to operate that in a system that maybe has a supply modulator that has a VCC max voltage of 3.4 volts and wants us to operate near about 2 dB gain compression. We can calculate a VCC rated of 2.2 volts, assuming an effective knee voltage of 0.4 of a volt from some of the empirical data. So basically, that tells us our power capability that we need to design into the PA. We need to design a 2 dB compression point that's at least equal to our P-rated target, and we need to design a 2 dB compression point at 3.4 volts that's at least equal to the P-rated plus the peak to average ratio where we want clipping to occur. So now I'm going to talk a little bit about the PA design that was done in this work. It was a band 13 PA, so basically the 780 megahertz band. The band 13 is one of the bands with the closer receive band offsets, minus 31 megahertz in this case. It was a 3x3 millimeter multi-layer laminate module. This PA was designed at about the time when the market trended to a smaller package size, so by today's standards, it's probably oversized for a single band PA. And we used a RF Microdevices in-gap HBT process for this PA. It's basically a two-stage PA. So in some of the CW measurements, we've shown some of these before in the earlier slides, but we've got our gain and efficiency plots, and we talked about the two VCC lookup table mappings earlier, two types of constant gain. In red, we can choose a constant gain at 30 dB that's maybe 1 dB into compression on the PAs. And in orange, we can choose a constant gain that's at about 29 dB, more like 2 dB compression in the PAs. And we can take those over, and at our rated power target, which in our case was 26 dBm, we can look at what efficiencies we would expect. So in this case, we see approximately 58% efficiency at the at 26 dBm when we use the constant gain near 30 dB. And if we go up to the higher compression level of 29 dB constant gain, we can see an efficiency of 60% at 26 dBm. So this is just the CW measurement data for the PA. What we found in our work is that this tends to be a fairly good estimate of what the actual modulated efficiency will be when we do run modulation and envelope tracking through the PA, typically within 1 percentage point of this measurement. So, to develop the data a little bit further, we collected a measured model of the PA and formed a static behavior model, and used that static behavior model in simulation to simulate the envelope tracking performance with these constant gain lookup table approaches. The simulation that we implemented was mainly targeted at evaluating PA performance. So the supply modulator in our simulation is primarily taking care of mapping the lookup table and doesn't really contribute to efficiency. Our goal here is just to evaluate the PA efficiency. So we set the simulation up to operate with the LTE 5 megahertz 25 resource block QPSK signal. We used about 1 millisecond of the LTE waveform in the simulation, and the same rated power target of 26 dBm. So these are some of the results of the simulation. This first result is the collector voltage in the simulation. This is a locus of points over time in the simulation showing the collector voltage actually applied to the PA. So it looks like the curves I presented earlier. You see at the high end it clips at VCC max, at the low end it clips at VCC min, and we have the constant gain curve through the central region. The second slide here shows some time domain data of the waveforms, just to illustrate that, I talked about earlier, it's pseudo envelope tracking. We're not exactly directly proportional to the envelope of the modulation, but you can see here that the collector voltage in red and in blue is the input signal to the PA, basically the modulation envelope in volts. And you can see that it does do a good job of tracking along. There's even I think this is just 5 microseconds of the waveform meant to show a demonstration of the characteristic. And if you look at, there's like a peak on the right side, like 3 or 4 peaks from the right, a large one where you can see the VCC max clipping is occurring. You can see where the blue actually exceeds the VCC voltage a little bit there. So in this ET simulation, we extracted as we mapped the VCC through the lookup table and feed the modulation through the PA. We calculated as a results of this simulation the AM to AM and AM to PM characteristics of the PA. And in red in this plot, I'm showing the gain of the PA versus the instantaneous power of the modulation. And what you can see is that there's a flat region in the middle part of the gain curve there at about 29.8 dB. That's where we're following the constant gain curve. So in this case, my constant gain was 29.8 dB. And then towards the high end of the curve, we encounter the VCC max clipping level. The voltage on the collector can't go up any higher, so then we fall onto that, whatever that max VCC curve is, we fall onto its gain curve, and our gain drops off. It doesn't drop straight off, it still has some shape to it, but we are clipping the peaks. On the low end also we can see the effective clipping. The lower, probably 1/4 of the gain curve, the gain actually raises up slightly above the 29.8 dB, and that's the effect of the minimum clipping being incurred. In blue, we show the phase characteristic of the PA as we're mapping the collector voltage through our lookup table. And you can see the residual AM to PM characteristic here. We've probably got 5 or 6 degrees of peak-to-peak phase deviation. Definitely could be better. This is probably marginal for this application. we were able to demonstrate some good ACLR performance with this, but if we had more time to work on this PA, we probably would do some work to try to improve that residual AM to PM characteristic. On the next slide, I show the modulated efficiency of the PA. This is still versus the instantaneous power being pumped through the simulation. And here you can see the more bowed efficiency curve as we operate on envelope tracking over most of the curve. And then at the very right edge of the curve, at the very high end, you can see the inflection point where we hit the VCC max clipping limit, and then we fall onto the traditional constant VCC efficiency shape. So this is still instantaneous efficiency. It's not time averaged yet, but we come up, we see we have a 58% efficiency at 26 dBm, which compares pretty favorably to what we saw in the CW measurements earlier. The constant gain that was used for the lookup table here was 29.8, so it was pretty close to that 30 dB gain case example I was showing on the earlier plots. On this slide, we show some of the simulation results as an average over time. So an output power of 26 dBm. The efficiency was very close to 58% when we did the time average over the 1 millisecond waveform, coming in at 57.9. The plot shows the spectrum of the waveform in terms of E-ultra ACLR. Our ACLR performance, we were seeing about minus 42 dB for ACLR1 and about minus 53 for ACLR2. So achieving better than minus 40 dB ACLR was within our targets for the project. Once again, this is simulated results, simulated envelope tracking results using a measured model of the PA. So when we do actually put it in the system with the envelope tracking modulator, it could be degraded further due to other imperfections in the system. Earlier, I've talked a few times about the residual AM to PM effect in the PA, in that basically we're left over with an AM to PM characteristic. We choose to use constant gain to try to linearize AM to AM, other than some clipping that we agree to add back in. But then this AM to PM characteristic that we have left over degrades our performance. So this slide is a comparison of two simulations using the measured behavior model, where we try to quantify what that difference is due to the AM to PM. So the red case is the same data that I just showed on the previous slide, where we use the measured model of the PA that includes both the AM to AM and AM to PM characteristics. And in the orange case, what we did is in the behavior model, we just mathematically set the phase characteristic to a constant. So it basically takes out any AM to PM distortion in the envelope tracking simulation results. And you can see in the spectrum that when we exclude that residual AM to PM, there is a difference in the spectrums. We are degrading our ACLR1 performance. Without the AM to PM included, we could get an ACLR1 performance that's more like minus 47 dB, about 5 dB better. I talked earlier that the AM to PM on this particular PA is a little bit marginal. Minus 42 is still a pretty good performance for ACLR1, but there's definitely room on the table to improve the AM to PM characteristic. So that kind of brings me to my summary and conclusion slide. So we talked a little bit about pseudo envelope tracking and constant gain operation. Tried to develop those theories into load line targets for the PA. And then we presented some results that we achieved on a single band solution PA that was able to achieve PA efficiencies of about 58% when we operated with a constant gain lookup table that was about 1 dB into compression, and that's for a 5 megahertz 25 resource block QPSK signal. If we were to operate at a higher level of compression, more like the 29 dB case that I showed earlier, we come in closer to 60%. That brings me to my final slide. So thanks for your attention. there's any questions, we can take those now.
Thank you very much for your talk. I have a concern is that when you build up the lookup table and it's based on a specific PA and you measured the PA and you have a model of PA and then you correspondingly you do the lookup table, that's fine. But however, in the product mass productions, you will have the process variations. And in this scenario, when you following this approach, building up the lookup table, how do you consider the variations and to include that in your lookup table? Is there any way like calibrations or
yeah, there's definitely a calibration in the system solution on every individual piece of hardware. So the lookup table is generated uniquely for each one.
So how sensitive is the lookup tables for the different
in addition to that,
classes?
We have run data where we collect a lookup table on one PA,
Right.
and we apply it to a second PA, and we can. I mean, it's not optimal performance, but we can achieve decent performance.
Okay.
So, but that is a concern, and is in the overall system there are hooks to try to accommodate that.
Oh, thank you.
Yep.
Hello, Liam Keys, TI. Thank you for your presentation. I had a couple questions. On your PA for the pseudo envelope, what's the relative bandwidth you assume on that relative to the actual modulation?
I'm sorry, what?
The bandwidth of the envelope, is it like 1.5 times the signal bandwidth? Or some of the earlier presentations they were talking about 5 times, 10 times to do complete envelope tracking.
Supply modulator, you mean?
Yeah, supply modulator, signal bandwidth.
Well, actually, my work's more on the PA side, so I can't tell you what our designers assume for that. So.
Okay. Then on the PA, for approaching like 30 dB gain, I assume you need 2 stages to get that. Are you modulating both stages or just the output stage?
It can be done. There's approaches to do it both ways. In this particular work, we were focusing on modulating the second stage, but there are other approaches that modulate both stages.
Okay. Thank you.
Yes. Can you go to slide 9?
Slide 9, okay.
Please. Yeah, so you talk about ACLR as your linearity measure. Can you speak to how this affects the EVM as well?
Well, for in most of our for the LTE wideband CDMA and LTE applications in RPA designs, traditionally the ACLR is the limiting factor as compared to EVM. What we did is we in the lab, when we evaluated system results, we evaluated ACLR as well as EVM, and that still, even with envelope tracking, that still held to be true, that ACLR for our types of applications was the limiting factor.
That's interesting. Yeah, I've been able to do a lot of PAPR clipping with no effect on ACLR and huge impacts on EVM, so I'm just kind of curious about that.
Okay.
Okay, thanks.
I have just a very quick question. You said it was a 2-stage PA?
Yes.
Did you connect, were the VCCs connected, or did you just control the output supply?
Yeah, that was the question that was asked earlier. But in
did
this
I
particular
missed
work,
it. Okay.
It can be done both ways, but in this particular work, we were focused on modulating the second stage.
Second, okay. Sorry if I missed it.
No problem.
We thank the speaker for the presentation.
Yeah, thanks, everybody.